All right, today we're going to dive into one of the coolest tools in all of engineering and mathematics, the Laplace Transform. Now, I know it sounds super complicated, but its real job, it's to make ridiculously hard problems way, way simpler. Let's see how it works. I mean, really think about that. What if you could take some terrifying differential equation, the kind that runs electrical circuits or describes how things vibrate, and just swap it for a problem you could solve with basic algebra? Well, that's the magic trick we're going to unpack today. What's funny is you're already totally familiar with the idea of a transform. Every time you take a derivative, you're transforming a function into its rate of change. When you integrate, you're transforming it into the area under the curve. See? You've been using transforms this whole time and probably didn't even think of them that way. But see, those transforms, they keep you in the same world, the world of calculus. The Laplace transform, it does something way different. It literally picks up your problem and moves it to a whole new world, a new dimension, where the rules are just easier. Okay, so let's get a handle on this idea. The best way to think of a transform is like a machine. You put one function in, the machine whirs and clanks, and out pops a completely new but related function on the other side. The Laplace transform specifically is what's called an integral transform. The engine inside our machine is built around this very special kind of integral, one that goes all the way from 0 to infinity. That's what does all the work. In this right here, this is the most important part. We take a function that's all about time, t, and we transform it into a new function that's all about this new variable s. We're literally going from the time domain to the s domain, or the frequency domain. It's like translating a problem from a really hard language into one you're fluent in. All right, it's time to pop the hood and see how this machine is actually put together. We're going to look at the formal definition, but don't sweat it. We're going to do it one piece at a time. So before I throw the big, scary equation at you, let's just look at the three main parts. First, you've got your input, right? That's your function, f of t, the thing you want to change. Second, you have the engine, this special exponential bit e to the minus st. This guy does the heavy lifting. And third, you've got the process, an integral that mashes those two things together and adds it all up over all positive time. And here it is, the whole shebang. That's the official definition. That fancy L just means the Laplace transform of, so this whole thing says, to transform f of t, you multiply it by e to the minus st, and then you integrate that whole mess from 0 to infinity. Whatever pops out is your brand new function, which we call f of s. Okay, theory is one thing, but let's actually see this machine in action. We're going to feed it a few functions and see what comes out. Let's start with the absolute simplest things you can imagine. First up, what if our function is just the number 1, a constant? We plug it into our integral machine, we turn the crank on the calculus, and what do we get? A beautifully simple new function, 1 over s. This is perfect. It shows you the whole process. A boring constant in the time world becomes a neat little algebraic thing in the s world. Okay, next test. What if f of t is just t? Well, now things get a little spicier. We've got to reach into our calculus toolbox and pull out a technique called integration by parts. It's definitely more work, but stick with me. The payoff is worth it. So after all that grinding through the integration, what's the final answer? Again, it's something wonderfully simple. 1 over s squared. You see the pattern here? We do the hard calculus just once, and we get a simple algebraic result that we can use over and over. So far, so good. We've handled some easy ones, but what happens when we feed the machine something with a little more character? Let's try a sine wave, the kind of thing that shows up literally everywhere in physics and engineering. So for a function like sine of 2t, the process gets, well, intense is an understatement. You have to use integration by parts, not just once, but twice. It creates this kind of weird algebraic loop you have to solve for. It is a genuine mathematical workout. I mean, just look at all those steps. All that calculus, all that careful algebra. You've got to be wondering, is all this really worth it? What could the answer possibly be that justifies all this work? And this is the payoff. After all that effort, the transform of sine of 2t is just 2 divided by s squared plus 4. We took this wavy, oscillating function, and we turned it into a clean, simple algebraic fraction. We tamed it.
Now, at this point, you're probably thinking, okay, this is powerful, but there is no way I am doing integration by parts twice every single time I need to solve a problem with a sine wave. And you know what? You are absolutely 100% right. There has to be a better way.
And there is. This is the moment where the Laplace transform goes from being this neat academic curiosity to an absolutely essential tool for every engineer and scientist out there. This is the secret. So let's just take a quick look back at what we did. The transform of 1 became 1 over s. The transform of t became 1 over s squared. And the transform of sine of 2t became 2 over s squared plus 4. See, in every single case, we took a function of t, did a whole bunch of calculus, and found its unique partner over in the S world. This reliable one-to-one mapping, that's the key to everything.
And here it is, the big aha moment. The secret is nobody actually does this from scratch every time. Instead, they use a table, a pre-calculated dictionary that just translates all the common functions from the t domain straight to the s domain. All the hard work has already been done for us.
And that is what makes all the difference. Using a table of transforms changes the whole game. It takes what we just did, that super tedious multi-step calculation, and turns it into a simple lookup. It transforms the whole concept from a boring classroom exercise into an incredibly powerful tool for solving real problems with circuits, control systems, you name it. So this leaves us with a really fascinating question. Now that we have this dictionary that can translate the hard language of calculus into the much easier language of algebra, what kind of impossible-seeming problems, like those crazy differential equations, can we now finally take on? That's where the real power of the Laplace transform is waiting.